This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
I'm probably speaking to the people that enjoy my lectures, but have you guys been watching the recordings? Is that clear? Is my writing legible, all that? All right, okay. Well, I think today the assignment's due again, so, and it's the introduction of a new thing, so, yeah, let's see. It is being released by 9 a.m. Yeah, I think 9 a.m. Yeah. But I'll explain. It's not about, the idea is to give you the assignment early so that you can then use it also to go, well, what do I have to get out of the lectures so that I can get it done on time. So it's all about sort of aligning the lecturing and the assignments so that you guys get the best bang for buck in the lectures. Here we go. This is one of those things where it's gonna cause me grief. I'm just going here. I don't need this. Yeah. Okay. Thank you all for coming. So today we're just going to start. This is basically a refresher for those who've done introductory physics, or you could see it as, this is my chance to catch up on some introductory physics before I start my remainder of the 5 weeks in the subject after Easter break. So it's just a very gentle introduction to basic relationships between different kinematics. Why is this not working today? Give me 1 sec. Oh, you're kidding me, right? Sorry. Something going on with the internet today that I'm not familiar with. I'll just go straight to the website then to avoid any pain. Yeah, so we're basically just a gentle introduction to just kinematics relationships that will help you pick up speed with the remainder of the 5 weeks of content on dynamics. Okay. So remember that the midterm exam that will happen in the first week back, the first Friday back from Easter, will be only about the last 6 weeks of lectures. It won't cover this content here. All right. So I'll go straight to, well, this slide here basically says what are the key learning outcomes. All I'm going to go through is talk about relationships between velocity, displacement, and acceleration. That's really what this lecture is about. And what do we mean by dynamics? Well, in all of the content we've done in the first 6 weeks, we basically analyze the forces that and the stresses that a biomechanical or indeed any mechanical system undergoes when it is held as stationary, subjected to some loads, where the forces are balanced and the moments are balanced so that there's no acceleration. We went through, in this, with this example, we analyze what must be the balance of forces at the joints and indeed the muscle forces for someone to hold a ball. Well, the rest of the 5 weeks will allow you to start studying, well, what must be the forces I need in order to make my arm rotate at a certain velocity, okay? That's the difference between statics and dynamics. Statics evaluates the balance of forces to keep something at rest, that keeps something at rest, but it's under mechanical load. And dynamics is about studying the unbalanced force that's needed so that I accelerate and make something move. All right. In this series of lectures, we will basically assume that our objects are rigid, so that we're only looking at the motion of rigid bodies through some motion. So we won't be investigating the impact of, well, not at least within the lectures themselves, we won't be connecting the content on mechanical properties into the dynamics. But what does happen, and this certainly comes up in your Year 3 Introduction to Biomechanics lectures, and also my subject in the master's level, you will see how these two things start to connect together. Why it's still important to study mechanical properties in order to evaluate dynamics. I guess the simplest statement to make is, if you find out what muscle forces you need to make something move, then you also need to know, well, what must be the mechanical properties of that muscle, and how much force must that muscle generate in order to make the arm move. So, unfortunately, this isn't a video anymore because for some reason my HDMI cable doesn't work. The HDMI cable doesn't work with my laptop that well. But basically, there's an entire field of research and industrial applications in the study of human motion, where you evaluate the forces that are needed to make someone move, in order to then develop implants, to develop new rehabilitation therapies for patients that are affected by stroke or something like that, or some other serious condition. And certainly there are people within the biomedical engineering department who do a lot of work in this space, particularly Dr. David Ackland and Professor Peter Lee have, and some of you may have also met Professor Marcus Pandy. They've really done a lot of work in this space to study and apply the understanding of human motion to clinical problems. So to really give you sort of a context of what we're doing for the remainder of the 5 weeks. The first 5 weeks, or 6 weeks, sorry, were about Law 1 and Law 2. And the remainder, we're going to do sum of forces equals mass times acceleration. That's really, that's the one law that we're going to, I mean, the other two laws still apply or are still important, but for this, for the remainder of the lecture series, we'll be looking at that concept. And you may remember this from one of my first lectures. You know, this is all statics over here, and dynamics is all about this. All right. What we'll start doing is initially work on this, and then I'll also introduce this to you through later in the remainder of the weeks. Please note that this I is different from the I that I just covered last week. Okay? The I that I covered last week is about the second moment of area, which is the spread of cross-section area. This I is the spread of volume, okay? Spread of mass across a volume. So, but I will again tell you about that in the remainder of this lecture series. So some terminology that we'll keep covering through these lectures. First one is the word kinematics. Kinematics is a word used that encompasses all the mathematical relationships between displacement, velocity, and acceleration. Basically, it's the description of the motion that a rigid body undergoes. In the first 6 weeks of lectures where we did statics, kinematics was about strain, right? Study of changes in length and changes in angle was kinematics of deformation. Here it's kinematics of rigid body motion, which is velocities, accelerations, displacements. Kinetics is the study of the energy and the forces required to generate these kinematics, or simple as that. Linear motion is when something is going in a straight line. Angular motion is when when a particle or all the particles that make up a rigid body, they are undergoing a specific rotational motion, i.e. there's an angle at which that they're turning through a revolution or something like that, or a curvature. Finally, general motion would be a combination of both linear and angular motion. So those are just some definitions. So can people here tell me the difference between velocity and speed? Yep, velocity has direction, speed is only a magnitude. Difference between displacement and distance is the same thing. We talk about the distance covered, that's the amount in meters, the length in meters that we've covered, whether it's left, right, or both. But displacement is a vector quantity. We know about acceleration. It is the rate of, it's given in meters per second squared. The most obvious, most obvious example is gravity. That gives you a constant acceleration of negative 9.81 meters per second squared. Inertia is just the tendency of an object to stay in rest or to be in motion. Okay? And so you'll hear me use that term quite often in the remainder of these lectures. Finally, what we're going to do is we're going to start studying kinematics of any mechanical system as if the mechanical system can be treated like a point. Okay, it's a little particle that we study its motion of, and so you'll be studying kinematics and kinetics with that assumption of, or with that simplification that the object is a particle. towards the last couple of weeks, we'll move it to studying that object as a rigid body. Okay, that's where the sum of moments equals I alpha becomes important. The equation about sum of moments. So initially, it just makes it easier to introduce you to these basic concepts by treating it as a particle, treating the system as a particle, a rigid body system as a particle. And it is a very useful way to analyze different mechanical systems that are in motion. So what I've put up here are some fundamental equations that I expect you to know, or at least learn within the next couple of weeks, so that we can use them routinely. In here, the notation U refers to displacement quantities, V refers to velocity quantities, and A refers to acceleration. And so these are, the top part gives you fundamental relationships between acceleration, velocity, and displacement. We know that acceleration is meters per second squared. It is the derivative of velocity, it's the rate of change of velocity, and velocity is the rate of change of displacement. So that's what's given in these three equations up here. A equals dv dt, v equals du dt, and then there's this one other relationship that you can you can derive, which relates acceleration, velocity, and displacement in one equation, which is A equals v dv du. Okay, and I'll just very quickly show you how that occurs, how we get to arrive at that equation, just for your understanding. And got A equals dv dt and v equals du dt. Whoop. Bring it down. Yep. If we write v dt equals du and then dt equals du over v, we can then write a dt equals dv. So subbing, we're basically going to sub this equation into this equation here. So a times du over v equals dv. So a equals v dv du. Okay? So that's a relationship that links up acceleration, velocity, and displacement in one go. I also want to refer you to two alternate notations that you'll see in these lecture note slides every now and again. Okay, for velocity, acceleration, and displacement. So we like I said, A is acceleration, V is velocity, and U is displacement. An alternative, so I should also say, you might say a V0 is initial velocity and V1 is final velocity, and Vf could be final velocity, while Vi could be initial velocity. These are all different ways in which you'll see me, and indeed other textbooks, write these different terms or variables for these terms. And the same for U. You could have U naught, Ui, Uf, those are all ways in which you might describe displacement. But another alternate one that I want to mention here, alternate symbols, let's call it. A is still acceleration. U and V are initial and final velocities. And S is displacement. Okay? So these are all another set of notations that you'll see. Okay? So I want you to be aware of that. And the way to look at those notes, and indeed this you'll find this in textbooks as well, you have to have an understanding of these kinematics, and then you'll be able to pick up what the differences are. Okay? So I want to go back here and mention these formulae here. So these bottom formulae are kinematics relationships when you have constant acceleration, where you got V1 equals V0 plus AT, and U1 equals U0 plus V0 T plus half AT squared. And I'll also mention that the other way you can write this is V equals U plus AT, and S equals UT plus half AT squared. Okay, so that's another, using the alternate terms. This is what you use. This I learnt when I was in high school, and I just never forgot it. It was just such a fundamental relationship that I like to come back to this one every now and again. All right. Oh, there's one more that I haven't mentioned in this slide, which is V squared minus U squared equals 2AS. Okay? And so that's a 2. I just want to make a note here, by the way, that these formulae I expect you to remember. Okay, these bottom formulae. All these kinematics relationships are fundamental, and we expect you to remember them, or know them by heart at least, if you don't know already. So these are now just showing, these relationships are now just showing you how, starting with the fundamentals of the differential, the relationships between acceleration, velocity, and displacement, you can go beyond just constant acceleration and start introducing concepts of changing velocities or changing acceleration. So here we've got acceleration as a function of velocity. If I wrote down f of v equals dv dt, that's the fundamental relationship, I can then come up with relationships for the time it takes to go from one velocity to another velocity. I can also calculate the displacement that I would have taken, or the amount of the length of time, length in space that I would have covered as I go over a certain amount of time. So here, the integrals v0, v1, these are your initial and final velocities, in which you're considering the time it takes to take the motion, the kinematics that's being described, and the same here, v0 and v1. So this is just to demonstrate that if you start from the fundamental differential equation relationships, you don't need to think about only constant acceleration relationships. You can actually think about these more complex relationships. So here we've got a runner. This is just an example. A runner runs 100 meters in 10 seconds. The position x over time is plotted on the left, which is shown here, and takes the form x equals 0.46 t to the 7 over 3. Determine the velocity and acceleration as functions of time and provide instantaneous velocity and acceleration after t equals 5 seconds. So I've got x equals 0.46 t to the 7 over 3. V equals dx dt, and A equals dv dt. Dx dt is equal to 7 over 3 times 0.46 times t to the 7 over 3 minus 1. There we go. That's given here. 1.07 t to the 4 over 3. And then dv dt equals 1.07 times 4 over 3 times t to the 4 over 3 minus 1. Okay. So A is given by that, and V is given by that. So I can then plug in t equals 5 seconds, substitute into V and A. I will arrive at V equals 9.15 meters per second. A equals that's what's given here, okay? So what I'll ask you to do now is for you guys to try to, for you to just, probably it doesn't even feel like a try for some people, but for you to just have a go at this problem here. So we've got a object that's being thrown up in the air, vertically up in the air, and it leaves the hand of this person that's throwing it at 5 meters per second. How long will it take to move upward before it starts falling down, and what's the maximum height it would reach? I'll leave you guys to give it a go for a couple of minutes. So hopefully it was fairly straightforward for most of you. Your initial velocity is 5 meters per second. Your final velocity before it starts falling down would be 0 meters per second. Acceleration is negative 9.81 meters per second squared. And then you can use these equations here to get at the time and the displacement. So for instance, I would write 0 equals 5 plus negative 9.81 times t. So 9.81 t equals 5. T equals 5 divided by 9.81 seconds. And I'll let you guys do the calculator solution. So you could use that one there, that relationship over there, to directly calculate what the displacement is without knowing time, but you could also do u equals v initial t plus half a t squared. So that's a third relationship that you could use to evaluate it. Okay? So notice here I have swapped between I've used VF, VI, and U instead of V, U, and S. Okay? So what I just covered before was for one-dimensional relationships. In 2D, it's not too different. Here, R represents a position vector, and the X and Y are components of that position vector. So, and the I and J are your vector indices, right? The X, Y direction. The dot on top of a letter, a bold letter, is typically denoted as a time derivative. So R dot is dr dt, V dot would be dv dt, and R double dot would be d2r dt squared, V double dot would be d2e dt squared. Okay. So what you're seeing here are vector notation relationships between position, velocity, and acceleration. So when you're doing your when you're calculating the velocity vector, you can, which is basically the derivative of the position vector, you can then take the derivative of each of the components as long as they are described with respect to time. So x and y would be functions of time. They would have a time variable in them for you to differentiate them. And in 2 dimensions, your magnitudes for displacement, velocity, and acceleration can be calculated using the component values using Pythagoras' theorem. So you've got position equals sum of squares of the x and y components, and same for the other two. Okay. So notice again, velocity and acceleration are vector quantities. When what you'll see me talk about in the lecture, the first lecture coming back, is how these velocity and acceleration vectors change when you have angular motion, rectilinear motion, simple harmonic motion, which are all, these are, we'll basically go through some fundamental motion characteristics, just like we did for fundamental deformation characteristics in the first set of lectures. So here's a quiz. If the position of a particle is defined by that equation there, what will its velocity be at t equals 1 second? You guys want to have a go? Anyone want to take a guess? Yes, that's right. Take the position vector, differentiate, you get the velocity vector, and so notice here that the 1.5 t squared plus 1 is my x as a function of time, right? That's x as a function of time, basically. And then 4t minus 1 is y as a function of time. And then I'm differentiating that and then plugging it in, plugging in t equals 1 second to evaluate 5 meters per second. So this is a final example where what we have is a particle that moves in 2 dimensions with coordinates x equals t squared minus 4t plus 20 and y equals 3 sine 2t. Determine the magnitude of the velocity and acceleration and the angle theta between these two vectors at t equals 3 seconds, I should say seconds. So what we do here is basically just use the fundamental concepts that I've walked through. So the position is written in parametric form in x, where you've got x as a function of t and y as a function of t. Then I basically take those relationships and differentiate and differentiate. So what you see here in the next slide is basically that solution process. We've got x equals t squared minus 4t plus 20, y equals 3 sine 2t. Differentiate, I'll get 2t minus 4 and 6 cos 2t. And then I differentiate again, I'd get 2 and negative 12 sine 2t. So at t equals 3 seconds, I plug the numbers in, and I'm basically using all the kinematics relationships that I've shown you in the previous slides to evaluate these the velocity and acceleration vectors. Okay. So in the tutorial sheet 4, the first 2 pages are basically lots of questions that just go through these concepts. So if you haven't done it in a while, or if you've never done it before, this week and the Easter break is your time to really pick that up, because these concepts are just so fundamental to everything that we'll do next. Okay. So that's the end of this lecture. I want to just make note again that on Thursday, Dr. Catherine Stock will be giving a guest lecture, and then Friday is Easter break, so there's no other lectures. The midterm test will only cover the first 6 weeks, so it won't include this content. At the tutorial this week, tutorial workshop session this week, you can do the tutorial sheet 3's bending moment questions. There's 3 or 4 of those that you can do in the class. That will help you practice what you learnt from last week. And I do urge you, if you've got the time and you feel the need for it, to go through the first 2 pages of the tutorial sheet 4 as well at the same time. Okay. Finally, I hope you've all seen my announcement of the midterm test, that the location is different from your usual lecture. And the last final thing to note is that the lectures, the remainder of the lecture content, the slides, will be uploaded during the Easter break, well before you come back. Okay, so I just want to make sure that we've got everything sorted out in that, and then we're done. Okay, thank you very much. I'll see you in a couple of weeks. All right, thank you.